Okay, so in the last lecture I showed you an overview of what we do with nonlinear partial differential equations, and I introduced to you three methods that we typically use. That's the Picard iteration, pseudo time stepping, and Newton's method. And what I would like to do in this lecture is that I walk you through the steps that we have to go through in order to derive the equations that we need for Newton's method for PDEs. It turns out to be a little bit complicated because we need to find the derivative of the residual. So let's say in the context of the Laplace equation, the residual would be something like f plus Laplace u. We want this to be equal to 0, and we're looking for a u that satisfies this. So if you have a nonlinear equation, so like for example the minimum surface equation that we talked about, then writing down the residual is easy, but computing the derivative of it that we need for Newton's method is a little bit more involved. And it requires calculus, so it's not, if you remember the definition of the derivative, it's not actually rocket science, but you have to go through this once to understand how it's done. And so what I want to do in this lecture is that I go through the various steps that you have to do, and then I'm going to show you that in reality it's not all that difficult, because there's the same kind of rules that you have for normal derivatives. So you know how to compute the derivative of x cubed, for example, being 3x squared. The same kind of rules that exist for normal functions of a function of x also exist for the derivative of a functional, or let's say of a nonlinear operator applied to a function u of x. But I want to go through the motions just to, let's say, explain to you how we arrive at these rules and how they're used. So this is lecture 31.55, Newton's method for PDEs, and like I said, I'm going to show this to you for the minimum surface equation. So we talked about this at the end of the last lecture, that when you want to solve the minimal surface equation, this is this equation here, we would like to write it in the form that we try to look for a root of a function. So a root of a function would be the place where the function is 0. So I'm going to introduce the residual, and the residual is just f plus divergence of this term here. So it's the same thing. I just take this whole thing, I bring it over to the right-hand side, and I ask for this to be 0. So r of u takes the role of the f of u, or f of x that we had in the algebraic case. I'm going to call it r of u because it's, well, we call it the residual. And then Newton's method is defined as follows. So we need to solve in every iteration. I'm given uk. I want to solve for delta uk, and delta uk has the following, has to satisfy the following equation, namely r prime times delta uk equals minus r of uk. And if I have delta uk, and of course I know the previous iterate, then I can compute the new iterate, uk plus 1. So in order to, let's say, write down concretely what I need to do for this iteration, I need to ask two questions. So first, these are all partial differential equations. I want to solve them with the finite element method, so I need to come up with some sort of variational formulation of this. And of course, as part of this, I will have to ask, well, what is this r prime of u anyway, right? So what is the derivative of a nonlinear operator r of u in the context of function spaces, of, let's say, functions u of x. So I'm going to start with the second equation, what this r prime is. So let's look at this again in more detail. So if I have r of u, and it's defined as this thing here, then r is an operator that takes a function, which in this case could be, for example, in the space h10. So let's assume that I have this rubber band or this membrane, and it has 0 boundary values, and it maps this solution u, or this function u, into h to the minus 1, right? So I have a function h1, I take one gradient, I take another gradient, that gives me h to the minus 1. So r prime is defined just like we always do, as the limit of epsilon going to 0 of, well, and this expression does not make any sense. What it should really be is r of u plus a perturbation minus r divided by epsilon. I need to fix this here clearly. So the only difference between regular functions and operators is that, let's say, when you work in infinite dimensional spaces, you do best if you don't write derivatives in terms of, let's say, a gradient or something like this, but you always think about directional derivatives. So I want to say this r prime of u does not exist as an object by itself, but only if you apply it to a certain direction. Okay, so r prime of u in direction delta u is defined as the limit epsilon going to 0 r plus of u plus epsilon times this direction minus r of u divided by epsilon, right? So think about this epsilon down here. So if I need to calculate this r prime this way, then I need to do a lot of calculus. So there's going to be nasty formulas in the following. You can go through it in slow if you want to. I'm just going to walk you through it. So I'm going to, so I have 1 over epsilon here that goes here, and then I'm going to just replace r of u plus epsilon delta u and r of u by the definitions. This is f plus this whole term, okay, and everywhere where u appeared, I need to replace it by u plus epsilon delta u minus r of u. That's this thing here. So the first thing is these f's here already cancel, okay. The divergence, I have a divergence of a times something, and I have a divergence of a times something. I can pull this out, so I get a divergence of a times the difference between these two fractions, okay. And now, when I want to look at the difference between these two fractions, essentially what I have is I have a function of x plus epsilon y. So think of x as u and y as delta u, okay. And then I would like to write this here in terms of something that doesn't depend on epsilon plus something that's linear in epsilon plus something that's quadratic in epsilon, and so on and so forth. So I want to do a Taylor expansion, okay? And while you can do this, it's not terribly difficult. You just have to write it down. What you find is that this thing here, I can write this as x divided by square root of 1 plus x squared plus this whole thing here in parentheses times epsilon plus terms that are proportional to epsilon squared. Okay. So if I do the same kind of expansion in terms of epsilon for this term here, you see that there's, so this term here, x divided by square root of 1 plus x squared, that is exactly gradient u divided by square root of 1 plus grad u squared. Well, that's exactly this thing here. So this term is going to cancel, and the next terms that appear is this thing in parentheses times epsilon plus terms that are proportional to epsilon squared. So what I get out of this here, out of this whole thing in square brackets, is this here. So divergence A, this corresponds to this, okay, plus terms that are proportional to epsilon squared. So each term in the parentheses here is proportional to epsilon. Okay, and if I divide this by epsilon, then the things here in parentheses do not depend on epsilon, and O of epsilon squared divided by epsilon gives me an O of epsilon. So the next step that I need to do is I need to take the limit epsilon going to 0, and of course O of epsilon squared divided by epsilon becomes an O of epsilon. Limit epsilon going to 0, that term disappears, and the only thing that remains is this here. Okay, so it's essentially just a Taylor expansion that we needed to do to understand what r prime of u in direction delta u is. Okay, so I mean it's a slightly more complicated expression, but that's really what comes out. So I showed you the long way of computing this by using the definition of the limit and so on and so forth, and then we just needed to go through the motion. In reality, there's a much simpler way to do this, because derivatives, or computing derivatives of operators in certain directions, works no different than, let's say, of algebraic functions. So for example, if your operator f of u is just a times u, then if you want to take the derivative in direction delta u, well, you just apply the product rule. So let's say a is a number, okay, so if you take the derivative of this, then this would be dA over du in direction delta u times u, okay, but dA over du is 0, okay. okay, plus a times du over du in direction delta u. So du over du in direction delta u, that's just delta u. Okay. The same thing is if I have, let's say, a square. I apply the usual rules. So there's an outer derivative and an inner derivative. Okay, the outer derivative is 2 times u times the inner derivative, and the inner derivative would be du over du in direction delta u. So that gives me 2u delta u. Okay. Same thing if I have, let's say, gradient u squared. Outer derivative is 2 times gradient u. Then I have to take the inner derivative, so d gradient u over du in direction delta u, and that gives me gradient of delta u. Okay, and I can make this arbitrarily complicated. So if I have 1 divided by 1 plus square root of u squared, the outer derivative is 1 divided by 1 plus gradient u squared squared. Okay, and the inner derivative is, well, the derivative of 1 plus grad u squared. That is, of course, 2 times grad u times the inner derivative of this, which is grad delta u. Okay, so you can really go through the motions. The only thing that's different is that when you say in a certain direction, when you finally apply all of the chain rules and the product rules, you always have a term of the form derivative of u with respect to u in direction delta u. Okay, so let's say if this was just an f of x equals ax, then you would just say, well, the derivative is just a, because the derivative of dx over dx is 1. And we always forget that, of course. But here, if I say the derivative in a certain direction, I actually need to say which direction it goes into. Okay, so in reality, computing derivatives of operators works exactly the same as it does for algebraic functions for all practical purposes. I'm not claiming that this is, let's say, mathematically super exact in all cases, but for all practical purposes, computing the derivatives works exactly as it does for algebraic functions. But I do have to pay attention that, let's say, at the very end, the most inner derivative is always du over du in direction delta u, and so I get a delta u here. Okay, so if you apply this here, if you think of this just as an algebraic function, let's say in terms of x, and this just being a particular symbol that acts on it, then you could have derived this whole thing here just as easily without going through the limit definition of the derivative. Okay, so I want to expose you to at least some of the terminology that we use. So we say that this r prime of u in direction delta u, we call this the Gateau differential of r at u, at the argument, in direction delta u. If r prime exists for all possible directions delta u, then we in fact say that r is Gateau differentiable. And you will be hard-pressed, let's say, in the context of PDEs, most of the things that you will ever encounter are Gateau differentiable. There are some cases where it's not. So let's say if you have things like plasticity, where you really have a kink, or let's say something changes behavior fundamentally at particular points, then maybe the things that you have are not Gateau differentiable. But most of the equations that you will encounter, let's say the Navier-Stokes equation, they are all Gateau differentiable. In some situations, under certain conditions, it will turn out that r prime is in fact linear and continuous in this argument here. Okay, so linear would mean that if I have r prime of u in direction, let's say, delta u1 plus delta u2, that this is in fact r prime of u in direction delta u1 plus r prime of u in direction delta u2. So if you have something like this, and the whole thing is continuous, then we can in fact say that r prime in itself is an operator. And in those cases, we often write it not as r prime of u in direction delta u, but we say that this is an operator here, so it would be r prime of u, and not just applied to a delta u. Okay, so these notations are often synonymous, and in, let's say, for many PDEs that we ever encounter, they are in fact the same. So let's come back to the minimal surface equation. So we talked about what r prime is, and so the second question then would be, what is the variational formulation of it? So I have to, as always, write it like this. To get the variational formulation, I multiply it with a test function, and I will probably want to integrate by parts. So now that I know what r and r prime are, I multiply the left side of I multiply the left side by a test function phi, okay, and I integrate by parts, so I get this whole expression here, okay, and the right side, this minus r here, I'm going to multiply that by phi as well. And so what I get at the end of the day is that my Newton step will require me to solve the following linear system for delta u, or the following linear partial differential equation for delta uk that appears here and here. uk, of course, is something that I have already computed in the previous iteration, and so this is the equation that I need to solve in every iteration. I want to end with looking at a few, let's say, practical considerations that you typically encounter when you apply Newton's method to partial differential equations. Namely, so if this r is already really complicated, and I mean, you might think that this r here is a complicated r, but in reality, let's say, you might encounter things where there's chemistry happening, where you have exponential terms, where you have multiple variables. Let's say there's not just one variable u, but you have a pressure and a temperature and so on and so forth. So if this turns out to be a really complicated form, then what you will find, of course, is that r prime is even more complicated. Okay, so you've seen this many times, that even for simple algebraic functions, the derivative can actually become rather complicated if you have multiple variables. So let's say in f of x and y, that is, I don't know, x e to the x plus log y times sine x or something. If you take all of the derivatives with respect to x and y, then the derivatives will become rather complicated, have a lot of terms. So if this is the case, you will almost always make mistakes. Well, maybe not, but it is quite likely that you will make mistakes calculating it, or even if you can write it down on a piece of paper correctly, then implementing it. And so the question is, how do you address this in practice? There are multiple ways how you can do this. So if you have a complicated form, I advise you to compute derivatives symbolically in packages like Maple or Mathematica, or well, there's any number of software packages that can compute derivatives. So it's often helpful to do this just to avoid the first of these error sources, namely that you might calculate it wrongly. Okay, but of course, then there's still the question. So now you've calculated the derivative on a piece of paper correctly, because I don't know, it's a printout from one of these programs, but the question is, how do you implement it correctly then? And there is a solution to this. So there is a technique that is called automatic differentiation. And automatic differentiation essentially means that in a code, you really only write a function that computes r of u, and you let the computer do the derivative and implement it for you right away. So you would write a function r of u, which you need anyway for the right-hand side for Newton's method, and you let the computer compute r prime as part of computing r. This is what automatic differentiation does. And I don't want to go into too many details here, but if you want to see how this works in practice, take a look at step 33. The step 33 deals with the Euler equations of gas dynamics. These are rather complicated equations, and all we need to do there is we need to implement r of u, and we get r prime of u for free and correct in that case. So another practical consideration is how accurate do we actually have to solve each one of these Newton steps? And the answer is, well, that's actually a really good question. So if you think about it, when you try to find an x here that, let's say, minimizes in energy, and so let's say your x1 is over here, and the x2 is over here, and the x3 is over here, and it does converge to the correct solution. Or let's say your u1, u2, u3, it does converge to the correct solution u here. the step that computes the increment delta U1 from U1 to U2 leads you from over here to over here. Both of these are far away from the exact solution. So you could argue that, well, maybe I don't actually need to compute this delta U particularly accurately. I mean, if it goes from here to here or from here to here, it doesn't really make a difference, right? We're still far away. All that we want to be is close in the limit, right? And so the approach that we typically choose for this is that in Newton's method, we typically compute the first few delta UKs on a very coarse mesh. And maybe we compute them with a fairly coarse tolerance. So let's say instead of solving our linear system to 10 to the minus 8, we only solve it to 10 to the minus 3. So we need, I don't know, 10 or 15 CG iterations as opposed to 50. And the whole approach to this is really that it doesn't matter what we do in the beginning. All that we need to do is ensure that we converge. And so, I mean, you can clearly argue that if we make mistakes because we're on a coarse mesh or we don't solve these linear systems particularly accurately, maybe I need 2 or 3 more Newton iterations to really get close to the solution. But that doesn't actually hurt us very much because these first few Newton iterations are so cheap. So what you want to achieve, let's say if you start on a coarse mesh and then over time you make the mesh finer and finer so you can get more and more accurate delta UKs, is that basically the first, let's say you need an overall of 10 Newton iterations, the first 5 basically counts nothing because they are on a coarse mesh where it's fast to solve. And all of the compute time is really only for the last 2 or 3 Newton iterations where you're on a fine mesh. So that's sort of the approach that we choose, and that's what I'm going to show you in the next lecture on step 15, how we achieve this. So the last sort of consideration that I want to talk about is we know Newton's method does not always converge. We need to start close enough to the solution for Newton's method to converge. And there are so that's a theoretical statement, and it is backed up by experience that in many cases Newton's method does not converge if you start somewhere. So what you need is something that is called a globalization strategy. Globalization would mean that you can start anywhere and still converge. That's what global means in this case. Okay, and there are 2 or 3 approaches to this. So one is called line search. One is called the trust region method. I'm not going to talk too much about this here. I just want you to be aware that you need to do this. Another globalization strategy would be to start with some Picard iteration steps, for example, until you're close enough, and then you start Newton's method when you're close enough. So to sum all of this up, if you want to use Newton's method for PDEs, you need to think about what the derivative of the residual actually is supposed to mean and how you can compute this. Once you understand what it is, you can derive it almost as you always do for derivatives. There's really not that much magic behind it, but I wanted to show you where it really comes from, so how it is defined. Okay. When you have it defined, then you would just solve a Newton iteration where the weak form looks like this. So phi times r prime applied to our search direction delta UK equals minus phi times the residual. Evaluated at the previous solution, that gives us the update. And then you compute from the update in the previous iteration, you compute the next value of UK. Okay. So this is a linear problem here. We're going to every Newton step should, of course, result in a linear system because that is what we know how to solve. And then when you have it defined like this, then Newton's method really proceeds like this, that you solve it on a sequence of finer and finer meshes with more and more accuracy. And in the limit, you should get to the solution of your nonlinear partial differential equation. So that's sort of the overview of what it means to apply Newton's method to nonlinear PDEs. These are the steps that we have to do, and then in the next lecture I'm going to show you how this looks concretely in an implementation for this minimal surface equation. So let's say, how do we assemble the matrix, how do we write the loop over K for the Newton steps, and how do we make it happen that we can start on a coarse mesh and make the mesh finer and finer as we go on. So that's sort of the practical implementation of the things that we talked about in this lecture. And the practical implementation is step 15. That's what we're going to do in the next lecture.